audio. If it's not, it might not record the audio. Uh, Did I hear that?
So just about every handheld power tool, such as this circular saw or this drill, have got a DC or universal motor in them. And in this video, I'll explain how they work. So here's my Ryobi hand drill, and on the front we got the chuck and some gears. And these are driven by the rotor, which fits inside the stator. So the rotor has got a fan on one side for cooling, and down here with copper windings in between, which are connected to the individual pieces of copper on the commutator. On both ends of the shaft we have a ball bearing, and I'm just going to put this in this block of wood here, and I'll hold that with a clamp. The windings in here and the iron core essentially form an electromagnet, and they're wired up to the commutator in such a way that if I apply electricity from here to here, the north and south poles here will be here and here. So let me demonstrate by applying a little bit of current, like so, and now I'll hold a compass on here, and you can see there's one pole here, and the other side has got the south pole pointing at it. And now the cool thing is if I move these around somewhere else, the north pole here is always going to be pointing to whichever side I'm applying that wire to. The thing with magnets is that north and south are always attracted to each other. So this magnet is trying to orient itself with the south pole facing north, because north is this way here. So now if I bring the south pole of another magnet nearby, that wants to reorient itself. And so if I bring it in from the side, whichever direction, it's always the north and south that are attracted to each other. So if I have the magnet like this and I bring this magnet in like so, it wants to rotate this way. This rotor forms an electromagnet, and if I apply just a little bit of current, in this case from a AA battery that I put some leads on with a rubber band, and I apply current here, we've got the north and south poles here and here. And now if I bring a magnet in from the side, it always tries to orient itself towards that. And you notice now it's spinning. So the cool trick is the north and south poles will always be this way, and with a magnet here it tries to orient itself this way, but as soon as it reorients itself, we're connecting to different contacts on the commutator, so north and south will still be this way, and so the rotation just is continuous. But as a motor, this is actually very ineffective because magnetic flux travels about 1,000 times better through magnets and through an iron core in here than it does through the air. And if I hold this near, I'm not really getting that much magnetic flux through here, and if I get too near, it just gets stuck. To give the flux a better path, I devised this thing here where I've got this bent piece of iron, and I've got two rare earth magnets here and here. And now if I put the rotor in between, I can have a much smaller air gap, although still pretty large for a motor, and the flux can then go around here, so I'll get much more flux going through everything. So let's apply the AA battery again. This time I have to go top and bottom because my magnetic poles are on the sides. And see, you can see it spins, but not terribly fast. Part of this is this rotor is actually made for a 110 volt motor, and I'm only applying 1.5 volts here. Partially what's limiting the speed of rotation here is that as this spins, it generates a reverse voltage just from the changing magnetic field going through the coils. So with this homemade voltmeter set to 1 volt full scale, if I now put the contacts here and I spin this, you can see I get a voltage here, and I can easily get up to about 0.6 volts. And that 0.6 volts works against the battery's own voltage, so cuts down on how much current I can get through. So now back to the power supply and 3 volts on my wires. Let's see how that does. So that already spins a lot faster, but let's turn this up, and now we're at about 30 volts on here, and let's try that again. Now that seems pretty fast, but in an actual drill, this rotor would be spinning 100 to 200 times per second. How powerful a motor this actually is a function of how strong this magnet is and how strong the magnets on the outside are. And this is just a very crude setup. In an actual drill, the magnet around it is very close and much stronger. And with the flux being able to go through iron about 1,000 times more easily than through air, there's a very small gap around the rotor so that we have a lot of flux going through here. Now what I was explaining is how this works as a DC motor, but this is actually a universal motor and it runs on AC. And the way that works is the stator, rather than having permanent magnets in it, actually has electromagnets as well. So with the AC reversing direction 60 times per second, if we had permanent magnets, it would just want to wiggle back and forth 60 times per second, but that's no good at all. But because the field magnets here also reverse in the same way, whenever the magnetism in here reverses, it reverses in here as well. So it's always in the same relative phase with each other, and so it continues to drive in the same direction. Now in a drill, we don't just use a couple of pieces of copper wire to connect to the commutator here. We actually use something called brushes, and we call these brushes even though they're actually just little pieces of graphite, and they go into holders here and here. Now these carbon brushes will slide much better and wear much slower than a copper wire would, but even these brushes wear out. So the brushes are always inside of a spring-backed holder like this thing here, so as the brush wears out it can continue to move forward. But of course eventually there'd be no brush left, and then the motor needs to be serviced, the brush is replaced. And that's why we never use a motor like that in applications that have to run for a very long time, such as a fridge or an air conditioner or a furnace. For things that need to run quietly and reliably for a long time, we use induction motors. This is just a simple shaded pole motor, much like the one that would be used to power the fan inside the freezer of a fridge. And if you look here, there is a stator with a coil on it, but there's absolutely no electrical connections to the rotor, so no brushes to make a lot of noise and get worn out. Induction motors vary from the very small to much larger. For example, this 2 horsepower motor for powering larger tools. In many ways, induction motors are actually simpler than universal motors, but the theory behind them is much harder to explain, so I'll cover that in my next video.
So what do we learn? Nothing. So the parts of a DC motor, this is called a universal motor, and these have to be designed that. The universal motors mean that these motors will run off both AC and DC. Now, why would you think DC motors are more expensive than AC motors per horsepower? Well, they both work off electromagnets. One of them's induced, one of them's not. So DC motors, we can't induce a voltage into anything, right? Because what's required to induce a voltage? Let me get a PowerPoint up here. So what's required to induce a voltage? So nobody in here knows what's required to induce a voltage. Need 3 things. Yeah, that's one. Usually magnetic field, right? So we got to have a magnetic field, which would be first, right? Not necessarily a coil, we need a conductor. And what else? We need motion. We refer to it as relative motion. One has to move. Now, what determines the amount of EMF we induce is the strength of the field. Number 2 is the number of conductor loops. And you could say in the coil, and then number 3, this would be the speed of the motion. And I put a voltage which provides a current onto this commutator. And we're only touching maybe 2 at a time, right? Understand? This comes out, goes to a coil right here. Then we have another magnet up here. It's either going to be a permanent magnet, so we have what we call permanent magnet motors, and then we have motors that have electromagnets. So let's look at an electromagnet, or let's just look at a permanent magnet. And we'll talk about the advantage of electromagnets in a minute. So I have an electromagnet over here, and this will always be a north and maybe a south. And like you said, we put them 90 degrees apart. This creates a magnetic field, either north or south, which causes this thing to rotate. Okay, but as soon as it rotates, what do I have in this thing right here? I got a magnetic field. There's my magnetic field. I've got conductor loops, and now all of a sudden I have what? Motion. Now what this does, it induces a voltage back into the armature that is opposite of the field that's being applied to the commutator. And we call this a counter EMF, electromotive force. Because it's always in the opposite direction of the current trying to go. So what we mean, I might apply a voltage here and here, which would cause it to run in other direction. Well, what happens is the induced voltage is plus and minus. So what it does, it has a tendency to cancel out. So what happens if I raise the voltage? What the motor does, the DC motor does, technically it would run at speed where the counter EMF cancels out the applied voltage, but it can never do that. What it's going to do is it's going to run at a speed where the motor can produce the torque that it's trying to produce. But if I raise the voltage, it means the motor's got to run faster to counteract the voltage decline. So what we can do with the DC motor is apply voltage. And we apply voltage on through, but the higher the voltage we have, the more current we have flowing through the coil, produces a stronger magnetic field. The motor starts speeding up. We got permanent magnets out here, right? You understand? They induce the voltage back into the armature, which we call a counter magnet, which is that determines where the motor stops. If I didn't let it happen, I put that on the DC motor, it accelerates and just tears itself apart. So what it does is when the counter EMF produces a counter EMF into that wire causes a voltage. If they cancel each other out, the motor will run. So they have to cancel each other out, but they get close, right? Yes or no? So raise the voltage, they're going to spin faster because they don't match anymore. They don't match. It means we got more voltage here than we have counter EMF. We have more current. Motor runs faster. They have cancel out the applied voltage. But not just got to have a little spin there to be able to produce enough torque. So we can control the DC motor just by doing what? Increasing the voltage on the armature. Increase the voltage, DC voltage on the motor speeds up, and then it'll go up to a certain speed and it just stops. I mean, it'll stop, it just runs at a constant speed, right? So we do what? If I lower the voltage, what does the motor do? The motor slows down. So we precisely control the speed of the DC motor. I mean, we can control it. We got feedback, which means we got a sensor out there that tells us what speed the motor's running. It's trying to control the speed of the motor just about as precise as possibly good. So if So if the armature voltage goes up, then the speed does what? Goes up. If the armature voltage goes down, then the speed goes down. Now, if we come over here and put electromagnet up here, then things change. Here we're dealing with a permanent magnet, which means the strength of the field never changes. It's a constant. And we call this permanent magnet motors. It's what's in mostly probably in your car, except for your starter, your starter, and series motor. As far as you know, the one in your car is still a permanent magnet. So what happens is if I come over here and increase the voltage on the on the field, what would you think would happen? So we increase the armature on the get more current in the field. The current produces a stronger magnet, which means it produces more counter EMF. So what happens if we change the voltage on the field? If the voltage on the field goes up, the speed goes down. You understand why? Because the field's stronger. So what determines the amount? The strength of the field. So what that means is if we increase the field, it produces more counter EMF for the same speed, which means the motor slows down. Because it's trying to run, technically it's trying to run at a speed where the counter EMF matches the applied voltage to something. Now the problem we have is that if that ever occurred, the motor wouldn't produce any torque. So, make sense? Of course, torque goes up. This is what's neat. So if I raise the armature voltage and I raise the field at the same amount, then what we do is we get more torque out of the motor. So what we can do, if we control both of them, we can control the torque of the motor. Now what torque is torque? You know what torque is? It's a rotating string. And the force we do, force with, pounds per inch or force per inch. So here we're creating torque. Our torque is turning the system. So if the torque goes up, it means the motor can run a higher load. Well, what we can do with the DC motor is if I go up with this and I go with this, we have a motor that runs at a speed that produces torque. And what happens if we lower the field down? So if the field goes down, right, then the speed has got to go up to produce the same counter EMF to cancel out the applied voltage. So speed is in the same direction as armature voltage, and it's in the opposite direction of the field voltage. We can use it to control the torque of the motor, and of course, we can use this to control speed too. Normally, we don't use the field to control speed, because what happens on certain motors, if you open up the field, the motor can literally run away. You might know why. So it's dangerous to try to. We don't want to reverse the field. We use a reverse armature. Well, what happens is DC. It's got these chunks of metal out there, which means these metal poles out there on the field has a little magnetism to it. You remove the field, you still have a very small field out there. The motor's going to have to try to run faster, produce enough counter EMF to cancel out the armature voltage. So in certain DC motors, it's run away from them. So what determines the speed of DC motors? How to get we can literally run DC motors extremely fast. But the problem is in a rotor that's coiled in it. drive motors up there running at 200 revolutions per minute on our hard disk computers. Has to be made very well, right? So AC motors, we don't do that. So DC motors, the limit on the DC motors, how fast you can work something to tell. So normally on some of the DC motors, we have what we call big old 200 horsepower DC motor. If you lost the seal, it would cut the motor off. And we never figured out we didn't want it at 200 horsepower DC motors. But we had one that gets up part of the loss on there. So I don't know if they ever figured out what we do. So the DC motor is proportional to the armature and inverse proportional to the field voltage. So what types of DC motors do we have? I was supposed to watch the lecture. Watching the rain. What types of DC motors? We have a shunt motor. You have a series motor. And we have a compound motor. So a compound is basically just a combination of the two. Then we have what we call a separately excited motor. It's just a variation of this. So a shunt motor, what we do is we take the field and then we wire it in parallel with the armature. So that's my brushes, guys. So I understand what the brushes do. So the brushes literally is what we transfer our power from the power source into that spinning armature. And what did he say? These things wear out. So the problem we have with DC motors is they literally are going to have to be maintained. And plus, over time, the commutator of the brushes, when they wear out, they'll get a little goop inside the commutator segments, and you can get short circuits. So they make a little burnishing tool that comes on the end of a kind of a stick. You can open up the side panels and put it in there while the motor's running and burnish and clean off your commutator. So the problem we have with DC motors, number one, they're a lot more expensive because the armature is wound. It's got a lot of copper in it. And the biggest advantage of a DC motor is we can precisely control the speed. And they run off DC. So if you got anything that's DC and it's got a motor on it, it's got to be a DC motor. So a shunt motor, what we do is we come over here and we have the field, and the motors in parallel with each other, and the armature in parallel with each other. And what's nice about a DC motor, to change the direction of rotation, so later on we'll look at this, because all you have to do is just change one of the fields. So if you reverse it, you change the armature and the motor runs in the same direction. But so you have to change the relationship between the armature and the field. And then the motor would reverse. So we have one whole lecture in the labs on how we reverse these motors. So what's nice about a shunt motor is that I come over here and put a certain voltage over here. Let's say 20 volts. And then, of course, that'll put 20 volts across the field. It would produce a certain amount of current. The motor would start spinning until it comes up. And when the counter EMF, or I'm sorry, the applied voltage minus the counter EMF, not quite zero, right? But it's shooting for zero, but it'll never see zero. Are we okay? Now, what would happen if the motor tries to slow down? Well, if the motor tries to slow down, it doesn't just produce, our speed goes down. Our speed goes down, the counter MF goes down, the motor gets more torque, right? You understand, and the motor will speed down. So the advantage of a shunt motor, and a lot of people call these constant speed motors. They try to run at a constant speed. Because if it slows down, the field voltage never changes, right? Understand? So if the slide tries to slow down, right? You understand? Then armature counter MF goes down, which causes the armature current to go up, which causes the motor to produce more torque, which causes the motor to try to speed back up to its regular speed. Now, of course, this is all within limits, right? So if you ever solve these things, your counter MF goes to 0, your armature current would try to go to maximum, and you turn things up, right? So DC motors are going to try to produce whatever torque required to run the load. It's going to be rated at a certain horsepower because that's the mechanics of the motor at the time. So a lot of people call these constant speed motors. Problem we have if the field opens, field voltage goes down to nothing, which means it's going to produce very little counter EMF into the rotor. Rotor's going to try to speed up, and this guy right here can run away if you lose your field voltage. If you lose your armature voltage, it'll stop. If you lose the field voltage, it will run away. It depends on what type of load you got. If you're running the motor unloaded, it will run away. No, it will run away, right? It takes off. Counter EMF never can match. Can't get enough counter EMF because all you have on your field is just the residual magnetism of the field itself. So what we do, we come over. So this is why when we reverse this thing, they very seldom reverse the field. Because what we're going to have to do is swap it, and if you have a relay that goes bad and it don't swap it, then the motor could run away. Everybody okay? This makes sense. So the next motor we have is a series motor. So a shunt motor has real good speed characteristics. This is a series motor. So the field is in series with the armature. These guys have extremely poor speed regulation, but they have really good torque. Really good torque. So I come over here, so we can't change the voltage applied to this, so we can still come over here and increase the voltage, the motor would speed up because you're increasing the field and this the same rate, right? Understand that? But what happens if the motor tries to slow down? If the motor tries to slow down, right, you understand that? If it slows down, counter EMF goes down, which causes the current to go up. Current goes up, which causes the motor to produce more torque. So your hand drill, anybody got a hand drill? Yeah. Now, if you got it up in there, it runs real fast. You stick it into something, it slows down, but boy, torque goes up, and you get some of these new hand drills. It'll rip it right out of your hand. Now, break your wrist. This is what the motor. This is what starts your car, a series motor. Because you're sitting there and you want to create a lot of torque. Series motor, very poor speed. Slow down. Like I said, anybody that's used a hand drill knows you hold it up in the air, it runs real fast. You stick it down inside a piece of wood, and all of a sudden it slows down, and then torque goes up. So these guys, any high torque application that you need, if you're not concerned with speed, then these are the guys you would use. These guys right here would be used if you're not looking for a lot of torque, but you're looking for pretty good speed regulation. Then we have what we call a compound motor. A compound motor is where we have a shunt field. and we have a series seal. So these guys have better torque than the shunt motor, but not as good as the series motor. It has good speed regulation, but not as good as the shunt motor. They have what they call a cumulative compound, and they have what they call a differential compound. One of them, the series, in the same direction. One of them, they swap it around. We're not going to get into those. One of them has better speed characteristics. One of them has better torque characteristics. But these guys right here, these are probably one of the primary motors in the industry. And what they do is they electronically control the speed. So we end up with these. So these are what we call compound motors. These are DC motors, guys. You'll still run into a lot of these, especially in the industry, because these were the motors for years and years and years. If I needed to control the speed and I needed to control the torque, this is what we used. You can electronically do that. AC motors, for years we could not control the speed on because we didn't have the electronics out there that would do it. Everybody okay? So these guys work off counter EMF. So what do we need to induce a voltage? AC motors. What type of AC motors do we have? Now, what advantage? Well, number one, AC. First of all, DC motors are more expensive per horsepower because most of your DC motors out in the field, it's not like your car. Most of the DC motors in your car are magnet motors. Well, it's not magnet. Most of your industrial DC motors are probably going to be so anytime you start dealing with a lot of pop, then you got to come here, you're talking about DC motors are very expensive. You got to buy an AC motor, you probably double the price if you did the same horsepower DC motor. So AC motors, what type of AC motors do we have? I got single phase. Three phase. And then what type of single phase motors do we have? We have universal motors. What's a universal motor? Yeah, DC or AC. And they have to be wound correctly by. What else we have? Well, we call it a capacitive motor. We have two of these. We have one we call a start, and then we have one we call a run. Then we have what we call a split phase motor. We have a shaded pole motor. I don't know if hopefully I got the shaded pole motor in here. We can take the pencil sharpener apart. It's got a shaded pole motor in it. Most small fans, AC fans, are shaded pole motor. Shaded pole motor. Any more on the list? I might have to bring up my PowerPoint. So all electric motors work off the principle of attraction and repulsion of magnetic fields. One or both fields must be electromagnets. So this is that one. So the field, technically, we call it the field, and the armature is the rotating part, right? Everybody understands what the commentator does for us now, right? It's just constant keeps that north and south. So what we have to do is we have to do something to make one of the fields appear to move, right? You understand that? So what we're doing here, we're constantly doing what? Switching it with the motor itself. So what he was telling me, we can take a switch and sit there and do like this, right? You understand, and cause it to happen. But we're letting the motor actually do what? Switch itself. And this would be a permanent magnet motor. So here's your shunt. This is the one we forgot. The separate excited. These are the ones I use most often in industry because we can control. Here we can control the speed, but we can't control the torque. Right? You understand? So separate excited are used a lot where we can have one power source running the field and one power source running the armature, and we can literally raise the field voltage and would cause the speed to go down, but the torque would try to go up. But if you do both at the same time, if you raise the armature by the same voltage, by the same percentage you raise the field voltage, you maintain the same speed, or I'm sorry, your speed would go up and your torque would go up. So I forgot about that guy. Changes armature voltage, change field voltage. Permanent magnets, we're pretty sure with that one. Series, we're okay there. Great starting and running torque, very poor speed regulation. This is probably one of the most efficient ways that we use. So used to run the speed of a DC motor, we would just control the armature voltage. And we would do it with devices called silicon control rectifiers, which are real weird. But what we're doing is we're moving away from a lot of analog stuff. We can't do it on sensors, but as far as control, over to digital something. So basically, the primary way we control DC motors now is something called pulse width modulation, which means we come up and we apply a certain frequency, and these are all DC. We apply a certain frequency, and you notice the frequency never changes. What's frequency? What is frequency? Yeah, but what is it? What is frequency? And it's not 50 here, it's 60 here. Huh? Okay. It's 50 in Europe. So what is frequency? So repetitive waveforms, we call each repetition of a repetitive waveform. We call the rate of the change. We call it frequency. So it's the number of cycles you have per second. And period would be the time per cycle. DC, we add something in there different for the duty cycle. So notice the frequency is not changing because the time's not changing. So this will probably stop when I mark on it. It didn't. So if I come over and look at these rise and edge right here, you notice they never do what? They never change. So the frequency is not changing. What we're doing is we're changing the amount of time that this pulse is what we call a high compared to the amount of time it's low. So what you notice, this is the DC equivalent. This is what the motor would see. So if this goes up, then the DC cycle, then the DC goes up. And if it goes down, then the DC goes down. We call this the duty cycle. So if I knew this right here was 1 second, right? Understand that? And then we'd say, okay, 1 second would be this. It's hard. And then we let it go for 50 milliseconds. We would say this was a 50% duty cycle. So 100% duty cycle would mean it would be solid DC. A 0% duty cycle would mean it would be nothing. A 10% duty cycle would mean it's going to be high 10% of the time. So DC goes up, and the DC motor will change speed. So this is primarily the way that we control DC motors right now. We control it with something called pulse width modulation. So now we can do it digitally. So this PLC, the digital device, we can program to develop pulse width modulation. So like the variable C drives, the AC drives, even though they're output in AC, you can set the speed with with what we call pulse width modulation. So now my PLC can control a variable frequency, or I can control the DC motor. Can you see the DC average is actually changing? So when this duty cycle goes down, the average DC goes down. And when the duty cycle goes up, the average DC the motor would see goes up. I'll try to show you all that. It's pretty neat. I'll do it. So we understand this, right? Armature. So the field, we can use it to control the speed, but it also controls the what? Torque, yeah. To reverse the DC motor, we have to either change the field, or we have to change the field connection or the armature connection. You can't change both. Okay. We used to have DC motor, we used to have the DC. We used to have the motor trainers over here, and that's what we'd do. We'd come up here and I'd swap the two leads going to the motor, and everybody'd say it's going to reverse, but it didn't get run in the same direction because I didn't do what? I didn't change the field in relationship to the armature, vice versa. Normally, the normal industry standard is to change the armature, especially on shunt motors. Because if something happens in your control circuit, and these contacts don't open, well, then the motor will stop. If it's a shunt motor and you disconnect, something happens to your field, and you still have an armature box, the motor will run away. So that's why the industry standard is to reverse the connection on the armature. And like I said, we'll have a complete lecture on how we reverse this. We'll look at reversing circuits. Basically, the reversing circuit for a DC motor and an AC motor are the same. It's just that you're somehow using contacts on the relay. You're going to change the connection on something. Okay? Yes, no? There you go. This is on Blackboard. David, you're not texting over there on me, are you? Okay. So the motor will not reverse if both the field and armature are reversed. So permanent magnet motors, we got no option to change the field because it's permanent magnets, right? You understand that? So we definitely got to swap the armature on those. Stepper motors, we won't look at that, which is a neat motor. Brushless DC motors, we won't look at that. These guys are starting to move into our actual. These guys are electronically controlled. So what we do on this one, the actual rotor is permanent magnet. And then we electronically switch the field around to make the outside rotor run. These guys are really efficient, but they cost more. You can see some of your hand drills, and they don't arc. So the problem with a regular motor, a regular DC motor, is you can't keep it from arcing at the commutator, where the brush is at the commutator. It'll arc, right? You understand, because it's switching. Brushless DC motors don't arc. So all your devices that use DC motors, like computers, all the motors inside a computer are all these guys right here. They're all brushes. Because you don't want arcs inside of you. A lot of electromotive, electrical interference, right? And these are actually targeted in hand drills. They're a lot more expensive, so compare a brushless hand drill to a regular hand drill, you'll see they cost quite a bit more because we have to add a lot of electronics to this. Because that inside field has got to be electronics and switch to cause these things to turn. I didn't know that one was in there. AC motors. So I didn't leave off, right? So capacitive start, capacitive runs, split phase, and shaded pole. Then we have three phase. We have a Y delta. We have a delta Y. We have a round rotor. And we have a synchronous motor. Now the problem we have with single phase is that in order for a motor to turn, a phase has got to shift, right? You understand that? So single phase, what happens, and these are induction motors. So what we have on this is we have a rotor, and there's no connection, no electrical connection between the stator and the rotor. I didn't bring my camera over here. But, I think I've already passed this around once. So. I know I passed the stator around. So this is a stator, and it's inside some type of frame. So when we're talking about the makeup of a motor, and we're talking about the field, and we're talking about the armature, you got to understand there's got to be some type of frame to hold the whole thing together, right? And then motors are going to have bearings because we got a rotating part that's attached to a stationary part. So on those devices, we use these things called bearings. I don't think I got a rotor for a DC motor. Come on. So this is a typical stator for an AC motor. And of course, these are the stator windings. So here the stator is an electromagnet. Okay. And you'll see these are laminated because these are the actual pieces that transfer the magnetic energy into the rotor. And it's got to be laminated. What do we mean by laminated? The problem, what's required to induce what's required to induce an electromotive force? Now that sounds like a good test question, doesn't it? Yeah. What determines the amount? So how does the regulator on your car work? So you notice your alternator on your car is connected directly to your motor. So it spins at the speed of your motor. So when you increase the speed of your engine, your alternator would put out more, try to put out more voltage. When you slow down, it would try to put out. So if we didn't do something, that means when I set up, everything in my car would burn up. Because remember, square. So if you don't speed on your motor, your alternator would not, everything would but you go out there and crank your car up and put your voltmeter across your battery, you see your alternator puts about 14 volts on that. You know, and your engine it put about 14 volts out there. Perfect. You can sit there and let it idle. It's going to put about 14 volts out. It's spinning the magnets, but it's spinning electromagnet. So your rotor inside your alternator is we don't have a commutator. We don't want to concentrate. So what happens is you got something out there you call a regulator. It's looking at the output of your alternator. It increases the magnetic field, which causes the strength of the field, which causes the alternator to put out some voltage. And the DC voltage will try to go up. Increases the strength of that spinning magnetic field, like regular, because what's constantly changing on the car. Yeah, Steve. So what does our regulator do? It plays around with that guy right there. So if speed goes up, then the strength of the field would go down. If speed goes down, then the strength of the field goes up. So that's the way your alternator is working. So all we're doing is just spinning something. So the problem is if my rotor, let's say a transformer. So a transformer, we're trying to transfer information or a power. We're trying to transfer information from something we call a primary and a secondary. The problem is to couple this, right? I've got to I'll wrap this around metal. So what do I have? I have a magnetic field, I've got a conductor, and then I've got motion. Well, the problem is your core would act like a short circuit because it's a big chunk of metal. But if I take that metal and break it all to pieces, right, you understand, and insulate them between each other, then all this current is not going to combine and create a short circuit. So what we do is we break up the core. Right? So this is on a DC motor because the DC motor is spinning through that tube. So what we do is we do what we call eliminations. So when you come up here, I pass this stator around. What you're going to see if you come in and look at it, you're going to see where that core is broken into hundreds of different pieces. And we did talk about transformers. So when I look at this thing, you can almost see them here. These things are broken into hundreds of little individual plates, which now we call them eddy currents, don't combine. So what it does is increase we don't want this guy here to be a conductor. We want it to increase we want it to concentrate a magnetic field. Now this is what's spinning inside of it. So what we do is we have these conductors right here, and then we have laminated plates. These are not laminated, and they're shorted out on each end. So what happens, if I put 60 cycles into this thing, what's that going to do? That's going to induce a voltage into these. It's working into almost a short circuit, which is going to create a real strong magnetic field in this guy. We're going to concentrate the magnetic field with laminated plates. But there's no electrical connection between the stator and the rotor. The voltage is actually induced into the rotor. And this is why these are called induction motors. And this spacing back here, even in there, it's very critical. In real life, they don't touch, right? You understand? It's going to be narrower than, I don't know. Now, the problem is, if I came over here and just put single phase on these things, then what would happen is this right here would be north, and it would induce a south because here it's coming out, right? You understand? Down here at any instant, this might be a north. This might be a south, and that would induce a north. And then they change. So the rotor would sit there, and then it would come over here. This changed. This would go to a south. This would go to a north. this would go to a north, this would go to a south, and the rotor would just sit there because it's going to lock into the magnetic field. So a single phase motor, if we didn't do something, a single phase motor would just sit there and hum at you. So what we have to do in AC, a single phase motor to move, somehow we got to create a shift in phase. And we've got two devices in electricity that we can deliver and put phase shift in. You can call a capacitor, or we can use what we call an inductor. So what we would do is we would have our field. I'm just going to draw it as one unit. Then we have our rotor. And then what we would do is we would come over here and we'd put another field over here. What we would do is we would put a capacitor in there. And we don't have a connection. So what happens is this winding right here, it's not phased with that winding right there. So what it does, it creates a phase shift that causes the motor to run or start. So that's what we call a capacitive motor. Now the problem wasn't that once the rotor is turning, it creates a phase shift itself just by the rotation of the rotor. So what happens, it means we have to leave that winding all the time. So on a capacitive start motor, what we do up here is we put a centrifugal switch that after the motor starts, and I wish we had one in here, like I said, we could actually see it. There's nothing on the back of that. That's a single phase motor. That's a step phase motor. It has two capacitors. One creates a really consistent power. It has another one that stays in all. That's the one we looked at right there. They had two capacitors on. These guys right here, they cost quite a bit more money, but they produce more horsepower for a smaller size. Not the only time you run these guys, they're usually time space. They can put a capacitive start motor in. They can if you want fit. Guys are used to get horsepower. You call it fast run. And these guys will have how many capacitors? Two. So that one I showed y'all with the capacitor mounted on the side, this right here is a 3-speed motor. So what determines the speed of an AC motor? Not the voltage of the light. You can, but it's very inefficient to try to control an AC motor with So the speed of a AC motor, the RPM of the field, is equal to 120 times the frequency divided by the number of poles. Or you might see 60 times the frequency divided by the pole pairs. And where does the 60 come from? Well, speed is rated in watt. What does RPM stand for? Yeah, revolutions per minute. How many seconds in a minute? 60. So basically, it's running in seconds, but the speed is in what? Minutes. So that's where the number of poles. So the smallest we could possibly have, and this we're talking about on the stator, would be a 2-pole motor. And we're running ours. What's our frequency over here? 60. So how fast would this motor try to run? 300, 3,600. So this motor would try to run at 3,600 revolutions per minute. Now the problem is, it's getting this guy right here, the voltage is induced into it. So what we start off, this guy is stationary, right? You understand? And you throw electrical power on it. We have a bunch of, and what determines the amount? Strength of the field, right? Number of conductor loops, which we can't do anything with that. I'm running loops. And then this is what we're doing, is we're doing 3, which is the what? Speed of the motion. So what happens, I put 60 cycles on this. This is stationary. It's not doing anything. The thing comes up and creates a lot of torque, pulls a lot of current. Then the rotor starts turning. If it can create enough torque to turn the load. Now this guy right here is 2 RPM. This guy right here is doing what? 60. So my rotor sees a speed of 58 cycles per second. The motor goes up. Speed of the motor goes up. The induced voltage goes down, because what are we doing? As the motor comes up to speed, we're constantly changing the speed of the motion. So what's being induced in the rotor is the difference between the speed of the rotor and the frequency that you're applying to the motor. So what this means is, technically, this motor is going to try to run, so the field on the outside is running at this speed, right? You understand? The rotor can never match that speed. Why can it never match that speed? Because you look at relative motion. Every motor has something called slip. So the rotor will never ever match the field speed, unless it's a synchronous motor. Induction motors won't do that. So I come over here and look at this one. So they're one of the ratings on a motor. It's not being recorded. I'm looking at this, and it's got the speed of the motor. It says this motor runs at 1725. So that's a 4-pole motor. So 4 poles, if I had 4 poles, then that's going to be RPM would be equal to 120. And what's our frequency over here? 60 divided by 4. That gives us what? Should give us half of 3,600, which would be what? 1,800. But the motor says its speed is going to be 1725. We call that slip. So an induction motor always has to have slip. Because if it doesn't, that means the frequency in here would counteract the frequency in there. Does that make sense? So all these guys always have to have slip. So how am I going to control the speed? I can't change 120, right? So if the field speed is 100 RPM is equal to 120 times the frequency divided by the number of poles, how can I control what's the normal? Now you can control these by voltage, but it's very, 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 very inefficient. You try to slow that thing down, the motor's going to pull a lot of current, right? To try to produce that horsepower. The ultimate goal of the motor is to produce the horsepower that it's rated at. It'll try to do everything in the world to produce that horsepower. So this is why you got a barrel got control on your attic fan. When you slow it down, you hear the motor start humming along. It's trying to pull more current to produce that horsepower, right? So how do we control what the best way or the most efficient way to control the speed of an AC motor? You change the number of poles. So when I look at this data right here, this is a pretty steep motor. There's the capacitor right there. These are brown sugar. These are common. These are yellow. And then I got three wires. How I switch between these wires, I'm changing the number of poles. This is a 3C motor. So all we do with relays is change which one of these now, depending on if you increase the number of poles. Make sense? You got to see what I'm saying? You say, what are you doing on that one? Changing the number of poles. If you ever look at the bar, see it's got three wires coming out of it. Every time you pull it, it switches over and changes the number of poles. So that's what you want to be the other way. So that's one way. But these are going to be fixed speeds. We can't have variable speeds. If we change the number of poles, these are going to be fixed speeds. So this is a 3-speed motor, right? So I'm just three different speeds. It's just like your system. You can only run it at 3 different speeds. Right? What's the other way I can do it? So what's the other way I could do this? There's 120 times the frequency divided by the number of poles. So what's the only other way I could change the speed of an AC motor? Change the frequency. And this for years and years and years was very complicated. So this is why for years, and you're still going to run into there, if you needed to control the speed of a motor, use the DC motor. But now due to what we have electronics, we can literally change the frequency of the motor. The problem is this guy's got a bunch of wires in it, and we call them variable frequency drives, which is basically incorrect. But that's the name, that's the industry name. The problem we have, and we got one of these back here, guys, I'll try to hook it up for you. The problem we have is that these coils, their opposition is set by 2 pi FL. So that means if you raise the frequency, the opposition of the winding would go up. If you lower the frequency, the opposition of the windings would go down. So what these drives do is they change the voltage and the frequency. So if the frequency goes up, what they do is they automatically change the voltage applied to the motor. They see voltage applied to the motor. The speed goes down. The frequency goes, the voltage goes down. And these things are pretty easy to program. You take what's on the nameplate of the motor, and basically you just enter that information in there. And then you can put how fast you want the motor to accelerate. And then you can either control it with the front panel, or you can control it with pulse modulation to actually control the speed. And these are dominating right now. So what advantage does an AC motor have over DC? One, cheaper for horsepower, a lot cheaper for horsepower. So what we were doing DC motors, we had electronic drive on DC motors, and we didn't have the motor. So now we have the electronic drive, which costs about the same amount, but now the motor is so much cheaper. So this is why AC motors are starting to dominate speed control. So now with the electronics, we can do that, but it can't just change the frequency. So this is what's named. I call them variable speed drives. So all these change with the frequency. As you learn up, the motor couldn't produce the torque and it would stall. As the frequency goes down, the motor would run up. So what they're doing is they're changing the voltage and the frequency on these things. So they're taking that system, converting it to DC. So what advantage does DC have over AC? DC well. AC wants to grab you. DC wants to grab you. Because all your muscles are controlled by electricity, right? You understand that? DC never really lets go of you. So once you get into a DC circuit and it causes your hands to do this, you brain without enough electricity to cause them to do this. So one of the problems with DC is that you get into a DC circuit, if it's got enough motion and current out there, your hands will lock on that stuff. You know, hopefully somebody's around. And don't grab them. We go pick up a 2x4 use nail to pull them out of it. Because if you grab them, you're going to be in the same situation, right? But that's just DC, right? First, we can predict it a lot easier. Chemically, we don't have to have motion. We can do it chemically, right? We can do it with light. With these things, photovoltaic cells, most people call them solar cells, where it converts the energy from light directly into DC, right? We're DC. We're DC devices. We do it chemical. We're creating electricity right now. So that's one advantage DC has. We can make it more easier. AC, you got to. How's all the AC produced? By spinning a magnet through coils. We got to have some prime mover. We got to make the generator spin. And what's the main ways we do? What's the biggest one? Most of the AC produced by steel, coal. In Alabama, luckily, we have a lot of rivers and stuff, so we have a lot of hydroelectric here. So what we do is we use something to spin turbines, and then the turbines spin motors. The biggest advantage of AC is we can electronically control it precisely. So what does the variable frequency drive do? It takes AC and converts it to what? DC. And then it takes the DC and converts it to AC at a frequency and voltage that we need. So we got the electronics that can handle all that power that's required by an AC motor. This is when variable speed drives really took off. Before then, it was DC motors. So if you get to an old plant, you're going to see a lot of DC motors. And you're still see them if I need to control both the speed and the torque. The advantage is AC. What's the biggest advantage of AC over DC? Induction. It automatically creates a change in magnetic field. Automatically. So we can induce the AC voltage. We can induce the DC voltage. These transformers. We can have transformers. We can have induction motors, right? You understand that? So induction, mutual induction is what we got. Okay, guys, go take a break. So this is the centrifugal switch right here. Well, this is actually the guy that causes it. So here's the counterweights. So as the motor starts spinning, these counterweights swing out. And when they swing out, it causes this plate right here to move. And then the actual switch is right here that rides on the plate. So I'll pass this around so you can see. Oh, that's a pretty good picture. So here's the actual switch right here. So that actually switches it, is it? No, it's right over here. There's the switch right there. Now this is the connection for the motor. So this is a pretty neat motor in that we can change its direction. So one of them is the field and one of them would be the start windings. Motor is the motor that can run on either AC or DC. So in this one, you'll be able to see. You'll be able to see the commutator, and you see what happened on this one. The commutator is actually totally burnt up. Right here, you can see it, and it's still got one brush, and then one brush is broke off of it. Here's the actual compressor right here. Here you go, Lynn. I've got a shady pole motor somewhere. Like I said, we could take the pencil sharpener apart. These are very, very simple motors. Um, but I'll show you the way the relay works. The problem we have with AC, and I'm trying to generate a magnetic field. The problem we have with AC is that it drops to 0 volts 60 times a second, right? Or 120 times a second. So how does an AC relay work? Well, what they got to do is they got to put something in there that creates a little bit of phase shift to maintain the magnetic field on the actual armature. So when I come up here, I didn't need to do that. So when I come up here and look at this, this is an AC relay. A shaded pole motor is about the same. So I know it's AC. How do I know it's AC? How do I know this is an AC coil? I can see the laminations. If this was DC, it would be a solid chunk of metal. So DC, we don't have to worry about the magnetic field inducing a voltage into my armature, right? But when we look at the tip of this thing, right here, and I'll pass this around, you see it's got a little wire wrapped around it. And what this is kind of like the secondary of a transformer. So what happens is when AC goes here, this creates a voltage in here that's slightly out of phase. And what this does, it makes the AC maintain that grip even when it goes to 0. A shaded pole motor, guys, works exactly the same way. So we'll look at like I said, I can't find it, so we'll go on this world famous, if anybody wants this. So you can see the little shaded coils right here on the very tip. Here, that's a good picture. I just put it on that table right there. I'm gonna have to put the motor back together. This is probably gonna. That's a pretty good picture. So this is a shaded pole motor. Now this is an AC motor. It's an induction motor. So if we look at the actual rotor, we would see it looks just like these, but it'd be a lot smaller. What they do is have a laminated core to actually concentrate the magnetic field. You can't hardly see the laminations on this picture. right here, this is what's important. This creates a device called an inductor, and all it is just a coil of wire. And this creates a phase shift, which causes this pole over here to be slightly out of phase with the pole on the other side, which causes the motor to do what? Rotate. So these are really, really cheap. They're very low horsepower, very low torque. We don't see a lot of these running fans. Like I said, it's running this pencil sharpener right here. Take the pencil sharpener apart. In fact, the motor that I have, I think I picked out of one of our pencil sharpeners because the actual sharpener on it. So we looked at capacitive motors, capacitive start motors. We looked at capacitive run motors. We looked a little bit at split phase motors. Split phase motors. And all the way to the first thing, guys, is to take the field off, get the part turned around, and put it on there. Change the shade over to the other side. We have slide going over to run off the shade over and so we did. We reversed it and put the numbers on there backwards. Everybody's coming in. Yeah, so what you do is you take the motor apart, you switch the shade over to the other side, and then motor reverse. We did a lot of things with clocks over there I'm not going to tell you about. Now, what's nice about three-phase induction motors is that the three phases are 120 electrical degrees apart. So that means three-phase automatically generates a rotating field. Rotates around rotator. So the biggest advantage of three-phase is a heck of a lot more efficient. More horsepower per side. They've always got a really nice phase shift that's creating nice torque. The problem is it's extremely expensive for power three phase out there, because that means all the on your pole, they have to have what? Three. Instead of running 2 wires, everybody have to run one. So any low torque, low power applications need only same motors. When you get into these big odds are all major companies have three phases. Now, two ways to wire a three-phase motor. We have what we call a delta, and we have what we call Y. So these are the phase shifts, by the way, created by the capacitors. This is a capacitive start with a centrifugal switch. There's a centrifugal switch. We call this a capacitive run motor. Some people call it capacitive start, capacitive run. We have to have that start capacitor in there. And we talked about this. So this is the speed of the motor. It's 120 times frequency divided by the number of poles minus the watt slip. So an AC motor cannot run at the same speed as the field. Because if it ran at the same speed, you wouldn't have a difference in speed. You wouldn't have motion between two magnetic fields. So you have to have slip. So when you look at the speed, there's an nameplate of the motor. That's the speed the motor would run at. You run it at its rate voltage, and at its rate. Let's say what, 1725. I know that's 24 pole motors. Okay. So the fastest we can run these things, we haven't changed or not. If we the fastest we can run these things is 3600 RPM. If you can run over faster than that, you can put it into 3600 RPM out of power. You don't want to run a motor faster. You don't want to put a frequency on it faster. You don't want to run an AC motor faster than what it's designed to run, right? They said maybe 10% over its rated. If you're using a variable speed drive, you got to be real careful. These high-speed motors that you see, these are still probably going to be DC motors. So the rotor has to spin slightly slower than the field speed in order to produce torque. So speed control, we only got two ways to control an AC motor. We can control the what? The number of frequency. You understand or not? So what would happen is the current in the motor would go down, the motor would stall, the frequency of the current in the motor would go up, and the torque would change. So some people call the variable frequency drives, they call them constant torque drives. They'll create about the same amount of torque that they do when you start and when you run. The biggest problem we have with this putting taking across the line is that it comes up, it pulls about 8 times its run current, right? You understand? And another thing it does, it creates 8 times the amount of torque. So that you got a 200 horsepower AC motor, and you put that sucker across that line, right? You understand? That sucker full try that thing can develop up to 1,800 foot-pounds of torque. You could tear stuff up to turn a what? To turn a 200. Do things to do that. We have what's called soft start circuits, which deliberately puts a lot lower voltage on the motor to let it start, so it don't create all that torque. Right? You understand? What's nice about a drive is that it's going to control the voltage and the frequency. So a lot of people call these constant torque drives. But you get the same torque when you start it and when you run it. And you can set the acceleration, and we'll look at why, what's going on there, right? Y'all understand that? So I think we've talked about this. Talked about 2 pi FL, so this is the problem we have. So we called it a volts-hertz ratio, and it's real easy. You look at the frequency on the nameplate, and you look at the frequency. The frequency it runs at, and then your will automatically compensate how much you need to vary the voltage and the frequency of the motor to run at a certain speed. So variable frequency drives are easier to program. Basically, you take what's on the nameplate of the motor and you take you enter the speed, you enter the maximum rated speed, you enter the frequency it runs at. Over here would always be 60, right? And you enter the applied voltage, what it wants to run at, and then it calculates everything else it needs. So we looked at this, right? Looked at this guy. This might be the picture of the one we got back there. Split phase motor, shaded pole motor. There's a shaded pole motor. 3-phase motors. So 3-phase motors, the actual field. So when phase A is going up, so if I was to draw these, and I'll draw these in different colors, and I'll try to do the best I can, guys. So we'll do phase A. I'll do that red. And then phase B, let's do that in blue. So 120 degrees is basically about here. So what would happen is phase B would be doing this. And then phase C, I'll do this in green, would be 120 degrees right there. So phase C would be doing this. Now I could complete all of them, but I'm not. So you can see what's happening is that when phase A starts going down, then phase B is coming up, which would cause your field to do shift. So what's nice about 3-phase motors is they automatically generate a rotating field. So we don't have to have star capacitors, we don't have to have inductors, we don't have to have shaded pole, right? This is one way we could wire it. This is our motor. This is a dual voltage motor. This is a Y connection. Now, if you're running a motor Three-phase motor, delta Y makes sense. We do have delta Y motors. They automatically produce a reduced voltage start for us. Right now, our motor right there is that a delta motor or a Y motor. Don't know, don't care. Because it's not a delta Y motor. Delta Y motor, you can wire it Y, or you can wire it delta. That motor right there is a three-phase motor. Is it Y delta or is it Y and Y? It don't make any difference. It's going to produce that horsepower at that frequency. So anything that's the delta Y motor, it's important to really know the difference between how we wire this. So this is our motor. Our motor is a dual voltage motor, which means we can wire the motor to run at two different voltages. So what advantage does high voltage have over low voltage? Less current to produce the horsepower. Right. And what advantage does low voltage have over high voltage? Starts with an F. Safer. So the lower the voltage, the safer it is. But it's going to take more current to produce the horsepower. So normally in the industry, if you've got both voltages available, you're going to wire the motor up to be high voltage, because that means you can run smaller wires. Your contacts could be smaller. So high voltage components are cheaper to install and maintain than low voltage devices. So all your high wattage devices at your house, what does it run off of? 240. Why? You can run smaller wires, right? And the control can be smaller, but current. Right? Most people, three-phase is more efficient, which it's not. It's just cheaper to install and cheaper to maintain. So if I wanted to wire this motor in high voltage, then what we would do is we would hook all the coils in series with each other. So what I would do is I would bring my three-phase in on 1, 2, and 3. So this would always be true. And then I would jump 4 to 7, I would jump 6 to 9, and I would jump 8 to 5. And this would be for the high voltage rating on the motor. So this is high voltage, and it shows we have a what? We have a jumper between what? L1 comes in here. We have a jumper between what? 7 and 4. See my jumper up there? I have a jumper between what? 5 and 8. Okay, I have a jumper between 5 and 8. And it says I need a jumper between 6 and 9. L1 and L2 is going to come in on T1, T2, and T3. See how that's wired? Now this would be for high voltage. So the motor we've got over there is rated at 440 and 2 volts. So now we're going to wire ours for low voltage. So if we wire for low voltage, then the coils are going to pull twice as much current. So instead of wiring in series, we're going to wire in what? Parallel. So here's high voltage. Where are you going to find this information at, by the way? If you've got a dual voltage motor. On the nameplate. You're exactly right. It's going to be on the nameplate that shows you how to do that. So it says I'm supposed to do what? Oops. Oops, that's delta. So it says I'm supposed to do what? So here's high voltage. It says I want to connect 4, 5, and 6 together. So 4, 5, and 6. So this has got the center common spot. So what we're doing now is making the second common spot. 4, 5, and 6. And then what does it say I need to do? We're doing this right here, 4, 5, and 6. It says I need to bring L1 into T1 and T7. So here's T1 and here's T7. So what we're doing is we're making two Ys, right? So I bring my next one into what? Here and here. And now I bring my next one into here and here. So what we ended up with, if you look at this, and we ended up with two of these that are wired in parallel. So now the current would be divided between the two. Here the current's going to be the same, but it's going to be 1/2 of what it was, right? So this is what we got right here. Oops, I guess this one would go right there. And then these two right here be connected. So we end up with two Ys that are connected in parallel. So a dual voltage motor, you have to wire either what? Low voltage or high voltage. You can wire for high voltage and you get low voltage. Motor will create the burn. If you put it high low voltage, you can get high voltage, you will burn. Because you're overload, hopefully you don't overload. Okay. Just memorize this. No, it's in books all over the place. The only thing you got to worry about is the nameplate. Normally these nameplates are either glued on there. If somebody moves them around, they get tore off. And sometimes they actually rip it on there, and after a while they get tore off. Especially if it's lower and you can rebuild. So you got to get this off. You got to rewire the motor for low voltage you're going to run it on. Everybody understand? Now, how you're going to do that? Now, ours is split